Hello, everyone, and welcome to today's session. My name is Reese, and I'll be your moderator for today. We're going to get started in a couple of minutes at the top of the hour. We're just waiting so everyone has a chance to join. If you haven't done so already, make sure you register for this session using the QR code that's in the corner of the screen now. You can also head to datacamp.com/webinars, where you'll find this session as well as all of our future sessions. And if you're watching on YouTube, we also have a link to the registration page in the video description as well, so go check that out. If you do want to code along live with us today, you will have noticed in the reminder emails that you received in your email inbox that there is a little bit of setup info for today. The setup info is listed in the video description and in the chat. I'll be posting a link to it again very shortly. But essentially, we're going to be running through a few slides at the beginning, so you've got some time to do a little bit of setup. But we'd recommend, as soon as, if you do want to code along with us live, check out the setup info doc right away and work through those steps. It should be pretty straightforward for you. Outside of that, if you have any questions, comments, or anything else, let us know in the chat. We're going to be spending the last 10 minutes of the session answering your questions, so please do stick around for that. And if you haven't done so already, make sure that you register for Radar, our upcoming virtual conference on the 1st of April. I'll be posting a link to that very shortly, but I'll put a link on screen now for those of you that are interested. You can sign up via the QR code as well, but just head over to, just search for Datacamp Radar and you'll find it. Brilliant. I'll repeat these messages for any new joiners very shortly, but until then, make sure you register for today's session. And if you want to code along with us live, please do check out the setup info document in the video description. Hello, everyone, and welcome to today's session. My name is Reese, and I'll be your moderator for today. We're just about to get started in about 30 seconds or a minute or so. We're just waiting for the last few people to join, and then we will get started. There is a little bit of setup info if you would like to code along live with us today. The info is in a document in the video description. I'll be posting a link for those of you watching on LinkedIn as well, but it's also linked in the resources document as well. So check out the resources document and then, look for the setup info link in there. We've got a few steps for you if you'd like to code along with us today. We'll also be sharing a link to the Google Colab notebook that we're going to be working in, so please do keep your eyes peeled for that. However, it is in the resources document as well, so please do check that out if you'd like to code along with us live. And with that, I think I'll hand over to our host for today's session, Richie. Richie, please take it away.
Hi there, data scamps and data champs. This is Richie. Very excited for this session today. The principle is actually very simple. So we're getting to the point where creating AI agents is getting easier and easier. But in order to make sure you don't release AI slop into the wild, there's an important step. You need to test your work. So today we're going to be learning about evaluating AI agents using the Arize platform. Our guest today is Laurie Voss, who is Head of Developer Relations at Arize. Welcome, Laurie.
Hello. Thanks for inviting me.
Yeah, great to have you here. And Laurie, you're a returning guest now. So you previously did a session on Llama Index back when you were VP of Developer Relations at Llama Index. I feel like we just need to make you change jobs every 6 months so you can teach us the entire AI engineering stack.
It's very convenient for you, isn't it?
Absolutely, yeah. I mean, maybe not great for your career if you move around often, but useful for our audience. Anyway, Laurie is a web developer turned startup executive turned data and AI evangelist. She's got 30 years of experience in tech and in education. So basically his job now is teaching people how to evaluate AI applications and agents. Beyond that, Laurie was the founding CTO at NPM. So he took that from a hobby project to 5 million active users. It's one of the biggest sort of I guess, JavaScript projects around. And he also previously served as CEO and CDO at NPM. So very esteemed guest. Please take it away, Laurie.
Thank you very much, Richie, for the kind intro. So yes, as was just mentioned, I used to spend a lot of time talking about JavaScript. These days, I spend most of my time thinking about what it is what it takes to build AI systems that actually work, and specifically how to test them. So what are we going to talk about today? We've got a nice stretch of time together, so we're going to cover a lot of ground. We're going to start with the fundamentals, what an eval is, and why you need them. Then we will set up the tracing with Phoenix, which is Arize's open source product. Phoenix is how you capture the raw data that you'll need to run evals in the first place. We'll build a simple AI agent using the Claude Agent SDK, run it, and look at the traces it produces. Then we'll write two kinds of evals: code evals, which are simple and deterministic, and built-in LLM evals, where a second LLM grades the output of the first. We'll also write a custom eval from scratch, and we'll finish with data sets and experiments, which are how you iterate on your agent and actually measure whether it's getting better. As Reese mentioned, you've been given a link to a notebook, and you should have got an email yesterday about getting some API keys set up. So if you want to, you can code along as you go, and I'll be letting you know when are the good times to get involved in your notebook with blanks in it. But first, what is an eval? Evals are basically testing for AI, and traces are logs for AI. I hate it when computer scientists come up with additional names for things, so I tend to say that traces are just logs. They're very, they're complicated, structured logs, but they're just logs that you would use for debugging any kind of application. You can write tests for regular code. Given this input, I expect this output. Evals do the same thing, but for AI outputs, which are never exactly the same twice. And just like logs record what your server did at runtime, traces record what your AI did. They are very detailed, so they capture every agent call, every tool call, every LLM invocation with inputs and outputs at each step. Traces tell you what happened, and evals tell you whether it was any good. That's your model for today. The vibes problem is the most common way that AI features get shipped today. The developer runs the app a few times, it seems to work, and they ship it. Then it fails on inputs that they didn't test. The usual fix for failing code, which is unit tests, doesn't work here because the same prompt will produce different text every run. Two different responses might both be correct. There's lots of ways to answer in natural language that are correct to the same question without being exactly the same string. So there's no expected string to assert against. So teams often fall back on human review. They watch it run. If it looks fine, they ship it. That doesn't scale, it doesn't catch regressions, and it doesn't run in CI. So that means there's some things that you can't do without evals. If you change your system prompt to fix a tone issue, then the tone might get better, but now you find the bot is hallucinating product features. Without evals, you can't catch that until a user reports it. With a faithfulness eval, you see the spike before you ship. Every prompt change potentially affects every kind of input that users send, and you can't manually test every combination. So without evals, you end up playing whack-a-mole. You fix one thing, you break another, and then you ship it anyway because you can't tell. Evals give you a number that you can track, compare, and act on. It is the difference between flying by feel and flying by instruments. There's two broad types of evals. There's code evals, which are deterministic functions you write yourself. They run in milliseconds and cost essentially nothing. They give you an immediate, unambiguous answer. Did the output parses JSON? Is the response under 500 tokens? Does it mention the thing that I asked about? There's also LLM as a judge evals, which use a second LLM to grade your outputs against a rubric, a set of criteria that you write. LLM as a judge evals are much more flexible. They can handle the kinds of questions that code can't answer. Is this response factually accurate? Does it stay faithful to the source document? Is the tone right for a customer service context? These are not competing approaches, they're complementary, and most real systems will use both code evals and LLM as a judge. So when do you use which? Use code evals when the answer is deterministic. Format validation, length limits, forbidden phrases, required fields. But use LLM judges when you need semantic understanding. A correctness eval asks, did it answer the question accurately? A faithfulness eval asks, does it stick to the source documents without hallucinating? And keep humans in the loop for failure modes that you haven't seen before, and to verify that your LLM judges are actually judging correctly, because LLMs are unreliable. So your LLM judge can also be wrong. Checking your LLM judge against human judgment is how you know how much you can trust them. This is what an eval result looks like. Every eval produces a score and a label. It's usually a numeric score, usually 0 or 1, and a human readable label like correct or incorrect, valid or invalid. LLM judges add a third thing, an explanation. Code evals don't produce explanations because they don't need to. The check is self-evident, it failed or it didn't. But a judge that says incorrect without explaining why isn't much more useful than no eval at all. The explanation is where the real value lives because it tells you what was wrong, what was missing, what the agent should have done differently. They give you guidance to help turn a failing eval into a prompt improvement. Here's what a real judge explanation looks like. Let's say you have a travel planning agent and you're running a correctness eval. The judge doesn't just say incorrect, although it says that too. It tells you exactly what's missing. There was no budget breakdown. That was the thing that you asked for and it wasn't there. It says the agent gave destination info and recommendations, which is fine, but the user asked about budget travel and there are 0 cost estimates. So now you have a concrete, actionable failure. You know what to fix in the prompt. And if you're seeing this same explanation across 50 different traces, you know you have a systematic problem and not just a one-off edge case. The explanation is what makes evals into a debugging tool and not just a scoreboard. This is the full loop that we're going to build today. You instrument your application, a few lines of setup code just done once, and then you run it. Traces flow to Phoenix automatically. You export spans, you run your evals, code evals for the simple checks, LLM judges for the semantic ones, and you log results back as annotations. Now you see systematically across every run where your application is working and where it isn't. You fix the problems, you run it again, the evals tell you whether it got better, and that is the loop. That's what we're going to build end to end in the next few minutes. So let's get started. Step 1 is setting up tracing with Phoenix. Before we can run evals, we need something to run them on. Phoenix is Arize's open source AI observability platform. It captures traces from your AI applications, every LLM call, every tool call, every agent step, with the inputs and outputs at each point. You can run it locally because it's open source, but today we're using Phoenix Cloud because it's the easiest way to get started. Phoenix Cloud is free to sign up, and it means you don't have to install anything beyond what's in the notebook or run a Docker container in a notebook, which is a thing you can do, but always seems crazy to me. So let's get started with the code. You should be able to open up the notebook link you were given earlier. It'll open in Google Colab, and you'll want to open your copy at the same time. You'll want to make a copy of the code along version so that you can code along as you go, or you can just follow along in my version. You're also going to need some API keys. The email that you got earlier should have mentioned that. You'll need one for Anthropic because to power your agents, you're going to need an LLM, obviously, and one for Phoenix, which is where you're going to store all of your traces. Setting up for both of those is very quick, so if you haven't done it, it's not too late to sign up now. The first call installs our dependencies. It's very simple. Arize Phoenix is the Phoenix SDK. That's our observability platform. Open Inference Instrumentation Claude Agent SDK is the auto instrumentation package for the Claude Agent SDK. This is how it knows how to capture traces from Claude agents. We have built integration packages with every popular framework that is used to build AI applications, and those integrations have automatically instrumented the code or rather have they pre-instrumented the code, so you don't have to write anything. We also bring in Arize Phoenix itself, which brings in all the things you need for Arize, and Anthropic, which lets you use Anthropic to judge the output of your agent in Phoenix. The Claude Agent SDK, if you haven't used it, is Anthropic's framework for building agents. The agents it builds can use tools, they can search the web, they can maintain conversation context across turns. So you can go ahead and run this cell, and it'll take a minute to install everything. So while it's installing, let me talk about what we're going to build. Today, we're building a financial analysis chatbot. You give it a stock ticker and a focus area, and it goes out to the web. It researches real current financial data and writes you a report. This is a thing that whole startups are being built around, though ours is going to be a very simple version of that. It's going to work in 2 turns. First, there's going to be a research turn that searches the web and gathers data. Then there's going to be a writing turn that compiles the research into a readable report. The Claude Agent SDK maintains conversation context between turns, so the writing turn has full access to everything that the research turn found, so we don't need to do any agent orchestration. And because we've set up Phoenix, every step is going to get traced automatically. Every search, every LLM call, every decision the agent makes. That gives us the raw material for our evals. If you've been coding along, your install should be done right now, so we can switch back to Colab. Next, you're going to want to set up your API keys. I'm using Colab's secrets feature, so my values are already plugged in. You can use it too, or since you're just looking at your notebook by yourself, you can just be naughty and paste in your keys. As I mentioned, you'll need an Anthropic API key that's going to power our agent LLM's calls. And also we use a different Anthropic model to judge how well the LLM calls went. You also need a Phoenix API key and your Phoenix collector endpoint, which in the Phoenix UI is called your host name. You can get all of that from your Phoenix Cloud account, all of which is at app.phoenix.arize.com if you haven't already done that. Now we register the tracer. This is the magic. It is 2 lines of code that set up all of your tracing for you. Every Claude Agent SDK call in your application is now automatically traced. The register function sets up OpenTelemetry, which is the industry standard for application observability, with a layer called OpenInference on top. OpenInference adds LLM-specific attributes, things like prompt text, completion text, token counts, which model was called, what tools were invoked. The auto instrument flag tells Phoenix to automatically find and wrap all of your LLM and tool calls. That is all you have to do to get your observability working. Now let's build our actual agent. We're building a financial analysis chatbot using the Claude Agent SDK. It works in 2 turns, a research turn that gathers financial data from the web, and a writing turn that compiles it into a report. So here's our agent setup. You can see our research prompt and our write prompt. They're very simple, deliberately simple for the first version of this agent. And you can see our agent options here. We're going to use Claude Haiku 4.5 as our model because it's fast and cheap, so it's great for demos like this. And the allowed tools call is going to give the agent the ability to search the web. The web search tool is built into Claude SDK, which is extremely convenient, so you don't have to use a third-party web search tool as we used to have to do when doing this kind of thing. The permission mode controls what the agent is allowed to do autonomously. As I said, the agent works in 2 turns, and you can see those 2 here. I'm not going to go into a lot of detail about how the agent itself is set up, because this workshop is mostly about evals and not about building agents. But the first turn sends the research prompt and tells the agent what tickers to research and what to focus on. The agent is going to search the web, read results, and build up its research. And then the second turn is going to tell it to write the report. prompts are critical. So this, if you are coding along, is where I want you to code along in your own notebook. See if you can write a better prompt than the very basic prompts that I created. See if you can get your agent to one-shot things, which will be fun. The Claude SDK client maintains conversation context, so the writing turn sees everything the research turn produced. So it's like having a conversation. Go research Tesla, then now write me a report about what you just found. A lot of this boilerplate you're seeing here is so that the output will stream as we go so that we can see what our agent is doing as it's doing it. We wrap all of this in an async function here with the Claude SDK client. And it creates a Claude SDK prompt. It sends the research prompt, it waits for the research to complete, then it sends the writing prompt and collects the final report. We also wrap the whole thing here in an OpenTelemetry span so that we can capture the input and output at the top level. If we didn't wrap it in one span, then Phoenix would still be capturing the inputs and outputs because it does that automatically, but it would show the two turns as separate traces, and we'd have to filter down to each one to test things. So this is saving us some time later when we grade how our evals are doing. So now let's run our agent. You can give it your own stop ticker and your own focus area. I've given it Tesla. And I've asked it specifically to talk about its financial performance and growth outlook. In your code log, you should go ahead and run this cell. It'll take a minute or two because the agent is actually searching the web and the LLM is doing multiple rounds of reasoning. You can watch what happens. The agent, in this case, searches for Tesla financial data, reads the results, decides if it needs more information, and maybe searches again. Then it writes a report from everything that it gathered. This is agentic behavior. The LLM is deciding what to do. It's not following a fixed script. It's deciding whether or not it's done enough research. It is deciding whether or not it's time to write the report. And every single one of those decisions is being captured as a trace. Here you can see what it produced, an executive summary, a financial performance table with real numbers, growth drivers, risk factors, analyst price targets, and a conclusion. This is all from a single prompt to Haiku, which is the cheapest and fastest Claude model. It searched the web, it found real data, and it compiled a structured report. This is not bad for a first pass. This is not bad, but not bad is a vibe. And we are here to replace vibes with numbers. So let's see what Phoenix captured. In my DataCamp Claude Financial Agent project, you can see all of the traces that I have captured. Here you can see the Tesla one, which is the first one that I captured. If I click into it, you can see the top level input and output, the research Tesla focus, and the output that we just saw in the notebook as well. You can also see individual components of what happened. So you can see the initial agent call, and you can see the individual web searches that went into producing this report. So in this case, it went into 3 web searches before deciding that it was time to do the output writing. So this is the key thing about tracing. We didn't have to add any logging call to our agents. We didn't have to wrap the tool calls. We just called register with auto instrument is equal to true, and existing open inference calls did the rest of the work. Every Claude agent SDK call, every Anthropic API call, every tool invocation, they were all captured automatically. Each row is referred to as a span, one step in the execution. So, like I said, at the top, you have the financial report span. That's the whole end-to-end run. And inside it, the nested agent turns. Here's what lives inside of a span. Each span is a structured record. A span kind tells you what type of step it is, and the input and output attributes contain exactly what flowed in and out of each step. Timing, metadata, it's all there. When we run evals in a few minutes, we're going to be pulling these attributes out of our spans and feeding them to our evaluators. The input becomes the evaluator's input, and the output becomes what gets graded. Now we need to generate some test data. To run meaningful evals, we need more than one trace. We need a body of data. In the notebook, there are 12 test queries covering different tickers and analysis types. I've already run these ahead of time, so we don't have to wait. So I can show you what they look like. If you want, and you're coding along, you can kick them off in your own notebook now. So let's scroll down to the test data that I set. This is exactly the same as the initial query that I sent. It's just there's 12 of them in a row, and then a little loop that runs them all. So you can see them running there. We've got 12 test queries here. Some are single ticker analyses on different focus areas: financial performance, revenue growth, competitive landscape, AI strategy. And there's one comparative analysis that asks about 2 tickers at once. This gives us some variety. Different tickers, different questions, different levels of complexity. That is important. You want to test your test data to cover the range of things that users are going to actually ask. So now you can see in Phoenix all of the runs that I created and run earlier. You can see the initial Tesla run plus the 12 test queries. Each one is a complete execution of our Claude Financial Analyst. So now we have the data, let's evaluate it. Step 4 is going to be code evals. There's going to be no model configuration here and no API calls. We're just going to be running regular Python. Let's write the simplest useful eval that I can think of. Our agent is supposed to analyze a specific stock ticker. So a good deterministic test is, does the output actually mention the ticker that we asked about? This is completely deterministic. Either the ticker appears in the text or it doesn't. And an LLM judge would be overkill for this. So let's just check. First, we get our span data out of Phoenix. That's this get spans data frame here, and that gets it into our notebook so we can work with it. The Phoenix client is how you talk to Phoenix from Phoenix code. It exports all of the spans from a project into a pandas data frame, and every row is a span. Every column is an attribute, so input, output, span kind, timing, token counts, all of it. What we do here is we filter to spans with no parent, meaning that they are parent spans themselves. So that means that we have the top level spans that represent one complete run of our agent. Then we rename our long column names to just input and output because that is what our evaluators expect. This is going to be our code evaluator. The create evaluator decorator registers this as a Phoenix evaluator. And the kind equals code flag tells Phoenix that this is going to be a deterministic evaluator with no LLM involved. The function receives the input and output from each span as plain strings, and it extracts the ticker symbols from the input using a regex. Then you see my implementation, which filters out some common uppercase words that look like tickers but aren't tickers, and then checks that every ticker appears somewhere in the output. If you're coding along, see if you can think of a simpler or easier way to do the same thing that I just did. A code evaluator returns a label and a score, so there's no LLM needed. There's no API call, it's just instant. And because it's a proper Phoenix evaluator, we can run it with evaluate data frame as we're doing here. So we can look at what output we got. We can see that 13 out of 13 of the traces passed this very basic evaluation that I created. Why does this matter? This matters because it's your first line of defense. It may seem very simple, but a good battery of deterministic tests can catch a lot of failures before you ever hit your expensive LLM evaluations. If your financial analysis agent was asked about Tesla and it wrote a beautiful report about Microsoft, which is an actual thing that went wrong when I was writing this notebook and creating this demo, then no amount of eloquence is going to matter because the answer is wrong. And you caught it instantly with 5 lines of Python. There was no API call, there was no cost, and it was very, very fast. That is what code evals are for. Code evals aren't just toy examples. In production systems, they are critical. If your app returns JSON, you can check that it parses. If you have length requirements, you can check the length. If there are phrases that your app should never say, like as an AI language model or I cannot help with that, then you can check for them. It's fast and it's cheap and it's completely reliable. So let's move on to step 5, which is built-in LLM evals. This is where it begins to get interesting. Code can check whether the ticker appears, but it can't check whether the analysis is good. Is the financial data accurate? Is the report complete? Are the recommendations well reasoned? Those are semantic questions, so you need a judge. Every LLM as a judge eval has 3 parts. A judge model, the LLM that does the grading, a prompt template, also called a rubric, which are the criteria the judge applies, and then data, the examples being evaluated. Phoenix keeps these 3 things separate, which means that you can mix and match. You can try the same criteria with different judge models. You can try the same judge model with different criteria. It is modular by design. And here's the good news, which is you don't always have to write your own judge. Phoenix ships with a set of built-in evaluators for common checks. Correctness checks whether a response is factually accurate, complete, and logically consistent. Faithfulness checks whether the response stays grounded in the source material. We're going to see an important difference between correctness and faithfulness soon. And there are tools, evals for tool selection, tool invocation, document relevance, all the things that you'd want to check in an agent application. These are battle-tested prompts written by the Phoenix team that often work out of the box. So let's set up the judge. We're going to use as our first LLM judge the built-in correctness evaluator. We'll have 2 lines of setup to create a judge model. It is, we set up our LLM, and then we set up our correctness evaluator by giving it the LLM. We're using Claude Sonnet 4.6 here to do the evaluation, so a model that is a little bit more elaborate, a little bit smarter than the model that is doing the reporting. And you don't have to use the same model that your app uses because it often makes sense to use a larger and more capable model as your judge. Then we instantiate the correctness evaluator with no template to write. There's no criteria to define. All of that is built in to the built-in evaluator. Phoenix has already built a well-tested prompt for checking correctness. And because we renamed our columns to input and output earlier, the evaluator can find them automatically. Now let's actually run the evaluation with the evaluate data frame call. It takes our data frame of spans and a list of evaluators. In this case, there's just 1 of them in the list. And it runs each evaluator on every single row of the data frame. The judge reads the input and output from each span and grades it against the rubric, which is a natural language description of what the judge should be doing. Notice the suppress tracing wrapper that we've put here. Because we are using Anthropic both to do the agent itself and also as the judge, Phoenix by default captures traces of the judge operating. So to avoid polluting my trace data with the traces of the judge, I have told it to suppress tracing when it is running the judge. So then we log our results back to Phoenix. We did this earlier with the built-in evals. I didn't call it out. But once you've done an evaluation, you have to send the results back to Phoenix. So you can see us doing it here. We turned our code evaluations into a data frame and sent it back. And we do it again here with our LLM as a judge. The log span annotations data frame call attaches each eval result to the correct span using span identifiers. So now when you look at a trace in Phoenix, you'll see the eval score right there next to it. So you can see our mentions ticker calls with scores of 1, and you can see our correctness with scores of 0. And in fact, if you look, you'll see we got correctness 0 in nearly every case. This is not a successful eval, but it is a useful result. What this has told us is that there's something wrong with our eval. It means that the built-in correctness eval is very strict. It is grading against general knowledge, stuff that it has in its training data, so it doesn't have context about recent financial events. Our reports cite real numbers from web searches that the judge can't verify. So unless the judge was doing its own web searches, which is a thing that we could have set up, it's going to mark everything as incorrect. This is a signal about our eval, not about the agent. We might have done better here if we had used the faithfulness built-in evaluator. The faithfulness built-in evaluator can check against your source documents. So we could have fed the output of our web searches to the faithfulness evaluator and said, hey, does it look like like Haiku wrote a report that stuck true to the results of the web searches that it got? But I was keeping this demo simple, so I did not do that this time around. But this is also a great example of why you might want to use custom evals, because you know more about your domain than the built-in evals do. So like I said, this is what you see in Phoenix. Every eval now has the scores attached, and you can sort by score to find your worst performing runs. You can also filter to show only failures. So in this case, I'm going to put in a filter that I already saw, and you can see that it's only showing me spans where correctness label was incorrect. That is nearly all of the spans. If you click into a failing trace, you can look at the annotations tab, and you can get the full explanation of what went wrong. So here it says that it was incorrect, and it tells us why it was incorrect over here. The output contains several issues that need to be evaluated. The report date is dated March 6th, which is a future date. This is the correctness eval being incorrect about things because it's only using its training data. But if it was a better eval, this would be a better explanation. The important thing here is that you are getting from your failure to the root cause of your failure in a single click. That is what this platform is providing you. You're not scrolling endlessly through logs. You're not clicking around to try and coordinate, what happened with your agent with what happened in the logs. It's all laid out for you. So built-in evals are your starting point. They give you an immediate signal without any prompt engineering, but they are general purpose. They don't know what your application is specifically supposed to do. In this case, the correctness eval does particularly poorly because it doesn't have the context of recent financial events. What we want is something more tailored to our agent. Our financial analyst should produce actionable recommendations, not just summarize data. It should tell the reader what to do with the stock that it's analyzing. There is no built-in check for that. So that brings us to step 6, which is writing a custom eval rubric. This is where you make evals that are truly specific to your application. Every eval prompt that I've seen that works well has these 5 parts. So let's go through them one at a time. Building a custom actionability eval for our financial agent. Part 1 is defining the judge's role. you give the judge domain context and tell it what kind of output it's evaluating and what that output is supposed to accomplish. The expert evaluator framing here doesn't really make much difference by itself. What matters is the domain context that follows. We're telling the judge this is a financial report, and what matters is whether it's actionable. Part 2 is explicit criteria, and this is where most people underinvest. Don't say a good response. List exactly what makes a report actionable. List exactly what makes it not actionable. You want specific recommendations, concrete risks with data to back them up, forward-looking analysis, and reasoning behind the recommendations. Specific criteria produce consistent judgments, and vague criteria produce coin flips. Part 3 of your eval should be presenting the data clearly. Use explicit labels and delimiters. Begin data, end data is a very common pattern. You'll see it in the Phoenix built-in templates. And if you're working with Claude, XML tags also work very well as well. Label each piece clearly. So user query, financial report. Clear boundaries reduce the chance that the judge confuses the query with the report or vice versa. Part 4 is adding labeled examples. This is the part people skip most often, and it's the part that improves quality the most. Include one actionable example and one not actionable example right before the data section. This is what an actionable example looks like in the template. It has everything: revenue growth, a PE ratio, expanding margins. It identifies a concrete risk with a number to back it up, and it gives a specific recommendation: accumulate below a certain price. That is what an actionable report looks like. And it works very well to give your LLM that example. And here is a not actionable example. It's not wrong. Everything it says is true, but it doesn't say anything useful. There's no specific data. There's no specific risks. It's not a recommendation. So now the judge has a concrete reference for what you mean by those labels. It's not just a description, but a demonstration. Giving examples dramatically improves consistency, especially on edge cases where the report is something in between. And part 5 is you should constrain your output. Make it binary, not rate this from 1 to 10, or is this actionable or not actionable. Numeric scales require the judge to reason about magnitudes. What is the difference on a 10-point scale between a 6 and a 7? That is inherently ambiguous, even for a human. Binary is clear. If you genuinely need more nuance, and then you can add 3 categories, something like actionable, partial, and not actionable. But start with binary, because simpler outputs are more reliable outputs. So if you're coding along, now's the time to see if you can build a judge. You can see the rules that I put into my own LLM as a judge here, but I've left you space to write your own rules. As you can see, the full template in my notebook has all 5 parts combined. There's a role definition at the top, there's explicit criteria, there are some labeled examples, and there are section delimiters of when the data begins and ends. And then it is constrained output, saying actionable or not actionable, which tells the judge to return a single label plus an explanation. Wiring it up is the same pattern as the built-in eval. Classification evaluator takes your template, your label to score mapping, so actionable is 1.0 and not actionable is 0.0, and then evaluate data frame runs the judge on every span. The custom part is the rubric. The machinery is identical to a code eval. Let's look at the actual scores that we got. Most of the reports scored actionable with a 1.0, but this one scored 0, not actionable. We can see this much more clearly in Phoenix itself. So you can see actionability in our annotations, and an explanation of why it was actionable or why it was not actionable. You can see what the judge says. The report provides an explicit buy rating. This is great. So all of the data is here in Phoenix. It doesn't tell you what to do with it, that's the, but sorry, if we had if we'd picked a non-actionable example, such as this one, you'd see that the explanation says what's gone wrong, which is that it stops short of issuing any specific investment recommendation. So it didn't tell us what to do with it, which is the thing that we told it had to do. And so that is why it gave us the non-actionable rating, which is exactly what we built this eval to catch. So in this line, you see me logging my results back to Phoenix, which is where how we were able to see the actionability reports. You can also filter down your results in Phoenix to just ones where the actionability was 0. So we can change this filter to actionability and change this to not actionable. And you can see that we've filtered it down just to 5 failing spans where the result was not actionable. The report has whoops, sorry. So an important thing about writing evals like this is that you should treat your eval prompts like code. They are sensitive to wording. Small shifts in your evals can shift your results significantly. So you should be versioning them. You should be testing them on examples where you know the right answer. And if the judge disagrees with your human labels on 40% of examples, for instance, then you know that your LLM as a judge isn't working. It's getting it wrong. Phoenix has a prompt playground where you can iterate on rubrics without touching code. And that is a very useful way to evaluate your evaluator very quickly and get to an LLM judge that works really well. This brings us to step 7, which is datasets and experiments. This is how you close that loop that I was showing you earlier. The problem with one-off fixes is you found some failures, you've read the explanations, you know what to improve, so you change the prompt, and then what? How do you know that your fix actually worked? How do you know that it didn't break something that was working before? If you just run the agent again on a couple of examples and eyeball it, then you're going back to vibes. What you need is a structured way to compare before and after your changes, and that is what experiments in Phoenix are for. As I showed you earlier, we can filter our traces down to just the failing ones, and then it is possible to select them and add them to what we call a data set. Here I could create a new data set, or I could select an existing data set to add these traces to. I've already done that, so I'm not going to do it again. But you can switch to the datasets and experiments section, and you can see that I've created this data set, which has the 5 examples of failing traces that I created before. So now that we've got that, we can test against the failing traces only. This is going to be faster and more efficient than running our entire test suite every single time. So now we want to improve our agent. You can see that I have created the agent again, and this time I have given it a much more extensive prompt that includes very specific guidelines about what it should do. This hopefully will improve the actionability of the outputs that I was getting. I've updated both prompts. So the research prompt now explicitly requires specific financial ratios, recent news, current price data, and competitive context. And the writing prompt explicitly demands buy, sell, hold recommendations, all of that stuff. You should notice what happened here, which is that we didn't guess at what to change because the evals told us exactly what was wrong. They told us actionability was the problem, and so actionability is what we're changing in the prompt. Prompt engineering driven by data, not by intuition, is the core of an eval-driven workflow. If you're coding along, now is the time to test your prompting skills. What would make a better agent than my second attempt? Prompting is a lot of the work of evals, both in creating your agent and in writing your evaluators. Given this improved prompt and substantially the same agent, we can now run our experiment. An experiment takes three things. It takes a data set, which is our set of saved failure cases. It takes a task, which is a function that runs the updated agent on each example, and it takes evaluators, which are the same evals that we've been using. So you can see me setting up my task here, which is just taking the input and output and setting it up. And you can see our evaluators where I'm calling bind. Bind maps the inputs and outputs to the inputs and outputs that are expected by my evaluators. The task is just a Python function. It takes an example from the data set and parses out the tickers and focus area as you saw. And run experiment runs the new agent on every example in the data set and scores the results. You can see that happening. You can see us getting our data set, and then you can see me calling run experiment here. The result gets automatically stored in Phoenix, so you can compare everything that's happening. So now let's look at our experiment view. I have just one experiment here, and you can see that our experiment has an actionability of 1 and still the correctness of 0 because we didn't get rid of the correctness evaluator. But what this means is that our new prompt has worked great. Our new prompt has taken 5 examples where the actionability was 0 with the previous prompt, and it is getting a perfect score of 1 now. You can click into the traces of your actual evals as well to see what happened when your evaluator was running and when your task was running rather, and what was being evaluated. So the experiment is not a black box. You can click into the traces just exactly the same way as you clicked into your traces earlier. So no matter how many times you run the experiment, you can always see exactly what the explanation was. So you can see example by example which things improved, whether the score went up, whether the score went down, and if you were running experiments after experiments, you get this pretty graph going along of your evaluation score presumably going up. In this case, I one-shotted it from being terrible to being perfect. But this is what you're trying to do with evals. You can see example by example what improved. Did we fix the failures without breaking the things that worked? That is the question, and experiments give you a clear answer without vibes. The eval iterate cycle is where the real value in all of this stuff lives, not the score itself, but the cycle. You run evals, you look at the failures, you read the explanations, and you identify a pattern. You adjust your prompt or your retrieval or your tool configuration, and you run the experiment. In this notebook, I one-shotted from a totally failing experiment to a totally successful experiment, but that is not usually how it's going to go. Usually, you are going to have lots of iterations of your prompt and lots of experiments to see how you go. The cycle is how you move from, I think it's working, to I can prove it's working. So just to wrap up, let's recap what we built today. We instrumented an AI agent with 2 lines of code. Traces flowed to Phoenix automatically. We wrote a code eval, which is a simple ticker check that costs nothing and runs instantly. We built a built-in correctness eval, which is 3 lines with no prompt engineering. And we wrote a custom eval rubric from scratch to check actionability, something no built-in template could cover. We saved our failures as a data set, we improved the agent's prompts, we ran an experiment to prove it actually got better. That is the full loop: instrument, trace, eval, and then iterate. Some strong advice here is that you should start small. You don't have to do all of this at once. You can start with just one code eval that is checking that your outputs have the right format. Then you can add one built-in LLM eval that checks for the thing that matters most: correctness, faithfulness, whatever fits your use case. Run them, look at the results, see what patterns emerge, and then build from there. The first time a regression blows up and shows up in your data before it reaches your users instead of after, you'll understand why evals are worth doing. So now is the time to try it for real on an app of your own. As I've mentioned, Phoenix is open source and free to use. And if you've been coding along, you already have a Phoenix Cloud account. These docs have, our docs have companion notebooks with runnable code for everything that we've covered today and more. And the link to today's notebook is, as you know, already in your chat and in your email. So thank you so much. If you've got questions, we've got some time now. If you'd like to follow up later, I am at celdo.com on Blue Sky. Thank you for your time and attention.
Wonderful. Yeah. Thank you, Laurie. That was very cool stuff. I very much enjoyed that. So we have got time for a few audience questions. Please do ask them in the chat. We'll get to those in a moment. Before that, short announcement. If you have not yet signed up to the Radar virtual conference on April 1st, please do so. It's going to be a lot of fun. We've got so many top speakers. We'll be talking about all sorts of stuff about how humans and AI need to work together. Link in the chat. Please go for that. Actually, before we go to audience questions, Laurie, I've got a question for you. So when do you go about writing these tests? Because I know writing tests tend to be left till the end of the project, like just before you put stuff live, you're like, oh, does it work or not? But there's also like a paradigm about test-driven development where you write the test first. Do you have a sense of, for AI agents, like when a sensible time to create all these tests and evaluators are?
That is an excellent question. As I sort of was suggesting towards the end there, the best time to write these tests is continuously as you go, but start simple. Because there's a time and place for vibes. When you are doing your initial development and you don't know what this agent is going to do at all, writing an elaborate rubric or 10 code evals would be a waste of time because your output is going to change too fast. So your evals and your code should evolve along with each other. You should be slowly building up a battery of tests. As your code gets more solid, as your agent behavior gets more predictable, your evals should be getting more and more strict. Okay,
I like that. So you're going to iterate on both things at the same time rather than just planning everything up front and then writing your code, or doing the other way around and doing no planning and then realizing you got a problem.
I mean, if I'm being honest and I'm looking at how Arize customers really show up, they do generally tend to wait until the end and then show up and go, this thing doesn't work in production, and so now we need some evals. But that is not how we recommend doing it.
All right, so there's theory and practice, and probably in theory you should be doing it earlier than you actually are. All right, so a couple of questions from the audience. The first one comes from someone or other, Luca. So Luca's asking about are there integrations with Arize for NA10 and Langflow?
Yes.
Maybe if you want to go more general, like what does Arize integrate with?
If you look at our docs, there's an integrations tab that we keep up to date. There's something like 40-something integrations in there. I couldn't possibly list them all, but basically every framework that you've ever heard of and every major LLM lab, we've got tracing built already. So your traces will just happen automatically. And in the unlikely case that you are unlucky and we don't have an integration for your framework, it is absolutely possible to manually wrap all of your calls in open inference spans. And we've put a lot of effort into our agent accessible docs. So you can ask your coding agent to do it for you, so you don't have to manually wrap all of your calls.
Okay, I love the idea of getting a AI to do it for you. Like, yeah, if you're using a weird tech stack, then yeah, probably still not too much effort to get this all integrated. Nice. There was a technical question about something we were doing during the session. So Big Blue Shoe says, when I try and set up the API, I don't know where the endpoint is. I think that was fairly early on.
Oh, I see. So Arize has two products. One is AX, which is our enterprise product, and one is Phoenix, which is our open source product. If you just went to arize.com and hit the biggest button that you can find, it sounds like you ended up on AX, which is why the instructions didn't match. If you go to app.phoenix.arize.com instead, you will get Phoenix Cloud, which is where the instructions work.
Okay, yeah. So I guess by default you're trying to be sold an enterprise product, which
Yes.
bit overkill for just the code along. Okay. So there was a sort of related question around this. It's like, what's the difference between like the free stuff and the paid version?
That brings us to AX again. So in Phoenix, everything is free. It is open source, so you can run it on your laptop and you will get everything that Phoenix Cloud provides you with. But if you are, an organization that needs things like compliance, or you need multiple teams, or you want monitors or real-time dashboards, those sorts of things are available in the enterprise version, which is called AX. AX also has a built-in AI assistant called Alex, who can do all this sort of stuff for you. And we are very busily improving Alex. So Alex gets better every week.
Okay, so especially if someone else like your company is paying for it, then you go for the pro plan. If you
Yes.
if you're paying for it yourself, then Phoenix maybe. All right.
Yes. Phoenix is the build it yourself option, whereas AX is the get Alex to build it for you option.
Okay. All right. One last question. So how does Arize sort of fit into the sort of wider ecosystem? So there's other tools like Langsmith. Basically, what's the difference? Akshay is asking.
So Langsmith is a competitor to Arize, so they do similar things. We integrate with LangChain and LangGraph as well. So you can use Arize Phoenix instead of Langsmith, and you will get all of the things that I've been talking about that you get in AX. So dashboards, real-time, Alex, real-time monitoring. One of the things that we find is a real differentiator for us is real-time monitoring. So once you've got out of the development phase and your agent is actually in production, you can send traces continuously from your real production data to Arize and have an eval that is running all the time continuously, monitoring whether your agent is doing the right thing. Because agents can slowly drift over time and start doing the wrong thing as they accumulate more data or people start doing weird things. When you're working with production data, you get to enormous scale very, very quickly. You get to huge, huge volumes of traces, and that is where AX really shines.
All right, so as you're scaling things up, yeah, that's where you start needing the pay plan and Alex and things to help build stuff for you. Okay, nice.
Exactly.
All right. With that, we are at time. So thank you once again, Laurie. That was cool stuff. And yeah, thank you to everyone in the audience who asked a question. Thank you to everyone who showed up today. Hope to see you all again soon. We've got more sessions to speak.